a great pleasure for me to be here and present some of my work to you. When I first got invitation from Professor Carl, I'm sorry, then I wasn't quite sure what to talk about because I didn't do anything, as you can tell. But all the work was done by my student. So since this is a Consumer Electronics conference, and I thought it may be a good idea to present the work I did in relation to consumer electronics. So in this talk, I guarantee that I will only have one slide with mathematical equations. All the others are images, okay? So the title of my talk is Perception-Inspired Video Processing for Ubiquitous Projection. And before I get into my work, I will first briefly describe, just in case you don't know me, briefly describe to you the research activities in my lab. I and my students are working on several areas. The first one is affective computing. We try to extract the emotion information from music, especially pop music. So hopefully later on, if I have time, I can show you a demo on that. And the second one is image processing for digital cameras, okay? And before I got into this area, I thought that working on something else or working on MPEG is the theme for, for image processing. But after I got into this, I thought that this is a very wonderful area. Image processing for digital camera is still an ongoing research area, and it welcomes a lot of new ideas. So hopefully I will be able to talk some of my work in this area as well in today's talk. And the third one is on video processing. My students and I spend a lot of time on seeking new technologies for video processing. It could be applied to display, or it could be applied to imaging. Okay, so this is why today the title of my talk is about perception-inspired video processing, and the last one is about multimedia communications. We worked on things such as digital rights management for digital TV, or video transmission over wireless, over internet, or even over power line. And it was this is the work that we did some time ago. I don't think I will be able to get into it today. If you want to listen to all this, we can have another occasion to go over it. So let me get back to the main topic of my talk today. It's about perception-inspired video processing. What does it mean? So I'm preparing this graph. It's as you can see, it's a photo of a foot, right? And one on the left and one on the right. Now I want to ask you, what do you see on the right, on your right? Yes? Well, the toes are coming out of the screen, right? And what about the image on the left? It's coming into the paper, right? All right? So if you don't see images like what I described, please go to see your doctor right away, right after my talk, all right? So this is what you perceive, but I want to tell you that, in fact, the left image and the right image are the same image. I simply just flip it over, not flip it over, just rotate it 180 degrees. Now to convince you, let me do this. I rotate it by 180 degrees. What do you see now? Are these two images the same? It's fantastic, right? So you have to we have to admire how our brain works. It's all coming here. It's all happening here in your brain. We interpret the image in two different ways. When it's pointing up, you interpret it as a negative image. When it's pointing down, then you interpret it as a positive image. Okay, and why is that? Okay, but I'm not trying to get into the theory behind this. This is done by people in psychology, but what I'm trying to do is kind of make use of such properties of human visual system for engineering work, okay? Now I want to do this experiment one more time, okay? Let me go back. Now this time I want you to stare at image without blinking your eyes. Let's do it one more time. Don't blink your eyes, don't close your eyes, just stare at this. It doesn't change, right? Until you blink your eye, then it changes. So this is how our eyes behave. It's very interesting, very fascinating property. Okay, I have another demo to show you. This is a well-known demo as well. You probably have seen something like this before. So let me play it. So what this shows you that it's a mask, right? And presumably, when the mask is turning 180 degrees, then you should see a hollow face. But instead, like you see that the face is coming out to you. It's concave to you, right? So this is not right physically. But perceptually, you do see it that way. Okay, so this again illustrates the fantastic power of human brain. Okay, so now we used to say that what you see is what you get. Perhaps you have to really think about it today after my talk. Right? What you see is not really what you get. I mean, the physical signal and the perceived signal are not the same. Okay, so this kind of I try to go through these two examples, try to motivate you that there's indeed something interesting in perception-inspired video processing. So in my title, I have this ubiquitous projection in there. Okay, what does it mean? Now it's kind of borrowed the word from communication. Right? In communication, we mention ubiquitous communications. Right? But here, we use the word ubiquitous to mean that the projector has to work everywhere. Okay, if I have a projector, a portable device, right, I can just point the projector anywhere in this room, for example, on the wall, on the ceiling, or on this background poster, and it should work. Now you can see immediately what the problem is, because in the living environment, we may not have a white surface all the time. Okay, and besides, it may not be flat. Okay, so how to get good projection image is a very important problem. Okay, and my students and I try to tackle this problem. We come up with some methods. Okay, but before getting to our method, I want to kind of briefly describe to you what other people have done. Okay, first, what does it mean by radiometric compensation? It simply means that we want to compensate for the color and texture of a non-white projection surface. Okay, in this room, we've got plenty of surface, right? Like the wall, like the floor, the wood floor, right? And in this example here, we also want to compensate for the texture of the wood panel. Okay, it's not an easy job. Okay, think about it, right? How to compensate for it. If you cannot compensate for this kind of texture, then you cannot get a good projection image. Okay, so we want to make any surface work as if it's a white projection surface. Right? It's a long way to go, but we made some progress, and that's why I'm here to report to you what we have done. Okay, let's try to see how this problem can be solved. Okay, because the surface is different, it has different properties. Now we have to understand what is the projection surface we are using. Okay, in other words, to solve the problem, we better equip the system with a camera. So we add a camera to the projector. Hopefully this is not a problem because cameras are dirt cheap these days. Do you know how much it costs for your laptop PC, the camera? How much does it cost, do you know? You guys are in consumer electronics, I suppose you know this. It's even less. It's even less. Okay, a few bucks, US dollars. Everything. That's why in Taiwan we don't make that much money. Apple makes money, but we don't. Sorry, excuse me, let me take off my coat. Okay, so since camera is kind of easy to get and it's quite affordable, so they add a camera to the system to work together with the projector. So we have a system that is called ProCam, which means projector plus camera. Okay. So once we have the system, then we can start to model it, right? But before that, let me tell you what is, tell you some background about the state of the art in different components of the system. First is the projector. Now I gave 2 examples here. I got it from, my students got them from the internet, right? They are so very small. The projectors can be made very small, and they are called Picoprojectors, okay? And you can also see projector in the popular and well-known Google Glass, right? And this is if you disassemble the Google Glass, and then this is the set of components coming out of the Google Glass, right? So I would like you to pay attention to this component, which is a display device, which project images onto your retina, okay? And this is a camera. Okay, so on this little device, this wearable device, it has projector as well as a camera. So it's also a ProCam system, right? So it should be, I think I must have convinced you that ProCam system is not a stranger to you. It's everywhere today, okay? Now this is the image you got, right? With Google Glass, you see images like this. Now, the image projected from the camera, from the camera on the Google Glass is overlaid on top of the real scene, okay? And you can tell that since the background is not pure white, there's going to be some color distortion. So how to deal with this problem? Okay. So here's an example of ProCam. A famous one is this Connect. You have camera, you also have a structural light source, right? And by working together, you can get some 3D information of the object. Right. And the top one is also another example. We have this author has 2 projectors plus, 3 projectors plus a camera for 3D acquisition. So the combination of projector with the camera is for imaging application. The purpose is to acquire 3D information of the scene. And here's another example. We call it virtual keyboard. And these were built by companies somewhere in the world. Okay. And they project virtual keyboard because actual keyboard is too big. So you try to use the imaging technology to project the image onto, for example, a tabletop, right? Then you got this keyboard. By sensing the finger movement, hopefully you can figure out which key this guy or this lady is touching on, okay, and so on and so forth. So this is a virtual keyboard application. And this is also for imaging application, for imaging purpose. Right? Then this is my last example. It's called virtual texture. People used ProCam system for graphics applications. In this system, you can project the light on the object, which is white, and then you project on it and try to generate appropriate shadow to simulate lights coming from different angles. Okay. All right. Enough of them. Then, here's one more. That you can turn any surface into a touch screen by using a ProCam system. Here are some examples. I think you can tell what they're doing right away. Okay, so ProCam system is kind of tightly coupled with the augmented reality applications. So what are the key issues or key components of a ProCam system? First is that you have to overcome the geometric distortion of the projection surface. So this is called geometric registration. Right. The second one is radiometric response estimation. You have to know the characteristics of the projection surface. Right. And then after you get that, you try to do color adjustment to get the appropriate or the right color out of the projection surface. The last 2 steps can be combined together, and we call it radiometric compensation. This is what people have done in these 3 areas. Right? For geometric registration, the purpose is to register a pixel across, register pixels between the camera and the projector. Okay? So people have used techniques like this. Here you see that this particular author, Professor Bimber in Germany, he projects different lights on the surface, and hopefully By appropriate operations, you can calibrate the geometry of the object and register the pixels. So originally, without any operation, you'll get an image like this. Then after the registration, you can get an image that appears correctly, okay? And then the exact technology is to shine lights on the object, and then and so on and so forth. I'm not trying to get into the detail. If you're interested, you can read all those papers. Okay? The second step of a program is to determine the radiometric response function of the projection surface and also of the projector and camera. Okay? So first, for projector, you try to relate its output pixel with its input pixel, and let's call that function FP. By the way, this is the only slide I have equations. And then for the projection surface, you also want to determine its radiometric response function, okay? And then now you have light shining from the projector, and that combined with the ambient light, okay? We call it A, and then that's the input to your camera. I'm sorry, that's the input to the projection surface, and the reflected light is C. So MI, that function, determines the input-output relationship between the projection surface. And lastly is the camera. You do the same thing. You try to find out the function FC that determines the input-output relationship between the cameras, of the camera, okay? So once these three functions are done, hopefully you can do a good job in radiometric compensation. The last, and the actual function look like this, okay? Then I'm not gonna try to explain, to get into the details of that. Now the last step is called color adjustment, all right? And a simple way is to try to determine the inverse function of the previous one. Like this one, once you determine this, then by taking the inverse of this function, you can determine the input, I, okay? So, and this is an animation. There's an animation here. So if project this original image onto the projection surface, and suppose this is the projection surface you are using, or it's a poster with these flowers, okay, with a tulip, right? And then you're gonna get the image like this. You're gonna see image like this on the projector, okay? And by appropriate compensation, right, then you adjust the input to be something like this. You project this on this surface, and hopefully the output will look like this. It will look right, all right? And this is an actual example from a paper by this author from University of Columbia. And the paper was published in 2004, so that's exactly 10 years ago. Well, obviously, what they have done is not good enough in my view. Okay, so I'm going to explain that a little bit later. Well, in the second part of this last step is the color adjustment. Okay, and this is a simple technique developed by Professor Bimber, which simply takes the inverse function, all right, and then by providing appropriate information into the function, hopefully you can get the correct image, I, all right, and this is the result you got. Now, if you watch closely, you're going to see some artifact here. You know, the boundary is not eliminated, kind of nice, not eliminated nicely, but it's better than nothing. Okay. All right. So, what are the key issues? You know, why we have to solve the problem, and what are the problems caused by what? You know, these problems are caused by what? We call it device limitations. There are mainly two things. First is the resolution. Projector has its own resolution. If the resolution is not high enough, you cannot do the job right, okay? And this is one example here. Right. Now, if this is the image projected on a white surface, I'm not sure whether you can see clearly because the projector is a low-pass filter, okay? And suppose it is the projection surface, right? Before any compensation, you got an image like this. And after you do something about it, and then this is the image you get. But this is not perfect. You know, a perfect one will look like this, right? And the reason is because that the projector doesn't have enough resolution. You blow this part up, you'll see image like this. If this kind of, you still see this kind of granular pattern coming out of the surface, right? And the problem is mainly because that, you have very limited resolution for the projector. So to do the work right, you have to have good projector resolution. Another thing is dynamic range, okay? Now this is one example with insufficient dynamic range. You project this image on this, then in the output, you're gonna see a little bit of the background, okay? That's not good enough, okay? So the dynamic range of the projector has to be high enough. Similarly, for the camera, the resolution has to be high enough, and the resolution has to be high enough as well, okay? This may increase the cost a little bit, but it's worth it. Okay. Now, I'm gonna get to our method. But before I describe the details of my method, then, well, I should say their method, because whenever I say I mean we. Whenever I say we, I mean them, all right? And them is my students, okay? So color perception. So here is one famous example. Let me ask you, what's the color you see here, and what's the color you see here? Are these two squares the same color? Please answer me. Are they the same? They're not the same, okay? But if I just extract these two blocks and show it on the black background, this is what they appear, okay? And it's due to the color constancy. You see these two squares are of the same color, okay? But actually, it's not. So here's a very good example. Although the physical signals are different, but their appearance are the same, okay? And it has to do with the context. In this example, this surface is brighter than this surface. And the brightness of the surface will determine the final color perception, okay? This is another example here. Let me do a little test here, okay? Please tell me which of the two colors is closer to this color. They are not identical, but one of these two is closer to this one. So in your view, which one is closer to this one? The one on the right, right? Okay, now let me cover these two squares with a gray background. Now, let's watch it carefully again. Tell me, which one of these two is closer to this one? Somebody say this, and somebody point to this. Make up your mind. Now, we did this test to many people, and majority says that this one is closer to this one. This is kind of yellowish, this is kind of more greenish, closer to this one, okay? Now, this is a perfect demonstration of the so-called context, right? If I put a color on top of a gray background, then the color may appear differently, okay? I have one more example. Actually, I have two more. And this is an experiment. In this image, please tell me, A or B, I'm sorry, C is closer to A or B, in your view. C is closer in terms of color. Do you think C is closer to A or it is closer to B? This is very interesting. People are hesitant to give their answer. They are afraid that they will fail the exam. C is closer to A or B? B, okay? Wow. Somebody's trying to make trouble for me, I guess. All right, then how about D? Now A is closer to D or B is closer to D? B, all right? Then this, whoops, I missed one example. You should have animation. But anyway, I'm sorry, I failed. I'm supposed to have animation to show you two slides and the other one with all white background, okay? Now it turns out that C is identical to B in this case, in terms of physical color. If you check the XY and RGB value of this area, it's actually the same as this block B. But yet you feel that this is closer to A. All right? And it has to do with the fact that I covered these two blocks with a gray background. Okay? And why our eyes behave like that? That's a very good question. So I'm going to give you answer a minute later. And this is another example. Okay? Now I want you to tell me which color do you see here? For this one, this square, this square, this square, and this square. What color do you think they are? Blue, okay. Then what color they are? Yellow. So if I cover up, I'm sorry, if I cover the other squares and just leave those squares on, then you see things like this. They are actually achromatic. They are gray. They are just gray. Yes. I'm not trying to fool you. This is a real experiment. Okay? Yes, it is. Okay? Now, in this first example, right, I say the context is that, the difference is that this is brighter than this area. Okay? In the second one, it's also about brightness, right? And these two are placed on top of a shaded area. Okay? It's about brightness. But this one is about color. I cover this with a different color. I place this cube in front of a blue color, and yet that will affect your perception of the color of these squares. Okay, this is my final demonstration. What do you see here? Now you have in this figure I have a blue background. Right? Then I have a little cross shape pattern. I place them on top of this blue background. What color do you see here for this central area? Yellow. That's what I heard, yellow. Okay, how about here? Blue. What if I tell you that the actual color is the actual color of this area, the cross, are gray? They don't have color. They don't. Okay, this is a famous Vasarely, I don't know how to pronounce this, but let me call it Vasarely illusion. Okay? So I say that when appearing in a uniform background of blue and yellow, the gray cross-shaped pattern illustratively appears to be yellow and blue respectively. Okay? This is a very interesting experience, all right? I guess at this point I have convinced you that this is a very interesting problem to work on. Okay? So the main idea is what? Our main idea is that color appearance is just relative to an anchoring color. It's called anchoring theory in psychology. Okay? And this human visual system property has to be applied to enhance image quality. Okay? Because in this ubiquitous projection problem, I want the projector to project the right image, right? The color has to appear right? So all these different factors I went through have to be considered. Now, I want to find a right tool to solve the problem. Now, it turns out just this simple theory is good enough to solve the majority of the problems. Now, you may have seen different names, of this, but in psychology, it's called anchoring theory. Okay? And this has to do with color appearance model. And people have been working on this for a long, long time. It's more than half a century already. The latest one is called, what's the number? Steadycam, I forgot the number, okay? But anyway, a color appearance model tries to relate a physical description of the color to the psychological description of the color, okay? Now, it allows you to kind of provide a proper input to the model and get the right color out of the system. Okay. Now, this is work done by H.Chen some time ago, okay? And they try to fix the color, and they simply apply this inverse function I mentioned earlier to for the color compensation, and this is the final output. Okay. Now from this, you compare this, you look at this carefully, you can see that the background color is kind of a little bit dark. Okay. And the foreground color is a little bit kind of too bright. Although these background dots disappear, but the overall image doesn't look quite right. Okay, and why is that? Well, this is about that. Just purely playing tricks from signal processing point of view is not going to fix the problem. All right, we have to take all these perceptual aspects into consideration in order to get the problem, solve the problem correctly. Okay. So this explains what went wrong in previous approaches. What they tried to do, well, let me explain a little bit what these graphs are. This is a color chart, color space, right? The horizontal, I'm sorry, the circular disk is about hue, okay? And this radius is about saturation, and this axis, the vertical axis, is about brightness, okay? And suppose this is the projectors, this shape, it may not be real, but this is just for illustration. This shape is the gamut of the projector, and this cone is the gamut of the image, right? Since you project this image on, let's say, a brown projection surface, and part of this gamut, image gamut, is outside the projection surface's gamut, okay? And what the previous approach tried to do is try to shrink this gamut so that it lies completely within the projector gamut. In doing that, you can see that there's a push from this somewhere here down here. So there's a decrease of brightness. All right? That's why you see image like this, the background color will become a little bit dark. Okay? And what we try to do by utilizing the perceptual property I just described to you, mainly the anchoring theory, what we did is this. You translate this cone, okay? And then you do the shrinking. And what's the net result of that with respect to the previous approach? The final cone here is a little bit larger than the previous one. And larger means that we don't sacrifice the brightness that much. And besides, it lies completely within the projector gamut. Okay, let me show you the results. This is an image projected on a white screen, so this is a reference, right? And the image has to look like this, right? If you project it on a magenta screen, you're going to get an image like this. Right? It looks kind of reddish. Right? Then you apply compensation to it. This is by previous approach. Then you see image like this. Well, I think it has done a reasonable job, except that this area, the details of this area disappear. Okay, and the color of the water, well, it wasn't quite right. Although you can see that, you may interpret this as white color. Okay, and this is our result. Okay, the details are kind of restored, and the color is much more closer to the original white color of the water. Okay, then how about this? If I project an image on a screen like this, left half is white, and right half is a wood panel, then you're going to get an image like this, right? You can see this kind of texture pattern on this image, right? And besides that, this is dimmer than this one because it has to happen that way, okay? Now, if you don't do this right, there's going to be some color clipping as well, okay? And we don't want to see that kind of artifact. And this is the result of our technique. Do you think it's good enough? If you think it's good enough, then my student can get his PhD degree. Otherwise, he's going to stay in the lab for a few more years. Pardon? Okay, so this is our current result. It can still be improved for sure. Okay, for example, this flower is a little bit, appear more red than this one. Okay, but if you compare with the original here, you don't do anything, just project the image on this wood panel, this is the color it's going to appear. Okay, this is more red than this one. Okay, so I cannot really blame my student that this is not as close as possible. No, this is not exactly the same as this one. Because the game here is not to reproduce the original signal. What we want is to make the image look as it's identical to the original image. Okay, it look identical, but that is not exactly identical. All right, so there's another problem you have to solve. That is the specular highlight, of a surface like this. And this is a table, right? And then when light shines on it, because it's glossy, it has glossy surface, you get the specular highlight. The specular highlight can affect the final color appearance of an image. So we came up with a method, originally, if you want to solve the problem, then you have to calibrate the image for each angle, every possible angle. We came up with a method that only require the calibration once, for example, at 90 degrees, then it can be applied to other angles. Okay, this is the result. Okay, this is the 90-degree compensated image. You project it at 60 degrees, then this is what is gonna appear. All right, but with our technique, it will appear like this. Right? Then again, it's not you cannot. It's almost impossible to recover the original image. Right? And I personally, I'm happy with this one because it has less red in it. Okay, so, excuse me, how much time do I have? 20 more minutes? Okay, enough, thank you. Let me move on to another application of the technique I just described to you. And it's about color enhancement for LCD. Many of you may know that the LCD consumes the majority of the power for an LCD, okay, for an LCD display. Okay, for example, in your laptop, LCD is the main draining source of the energy, right? So to save the energy, we may want to turn the power, the background power, down a little bit, right? But by doing that, you also decrease the image quality a little bit. So the name of the game is how to improve the image quality without affecting the energy efficiency. Okay, so this is an illustration. At 100% backlight energy level, this is the color you're going to see, and this is a gray color you're going to see. If you project image under 100% backlight, it may appear like this. But at 10% or even less, the two colors will appear very close to each other, okay? And then this is the image you're gonna get. You almost cannot see anything in there, okay? So how to recover or restore the image so that it will look much closer to the original image. Now maybe many people have done this, have tried to solve the problem, but we try to come from a different angle, as I told you earlier, right? From this perceptual aspect, okay? Perceptual point of view. Okay, so objective here is to preserve the color appearance across different displays or viewing conditions. Okay. Now, this is the result we got, by applying the same theory I described to you. Okay. This is the original color. Okay, and this is what it appears. It is a simulation of low backlight condition. So I covered this with a gray background, and this is what it's going to appear at, let's say, 10% backlight. After processing, it will appear like this. Do you see any difference? Good. You don't need to see a doctor. Okay? Then let me give you another example. I changed the color a little bit from green to blue, and this is before compensation, and this is after compensation. Again, do you see any difference? I think it will appear better on my screen. Okay, but hopefully you can see something there on that big screen. Okay, this is a real image. Before compensation, this is after compensation. Before, after, before, after. Okay, again, here you can do something, but you cannot really bring the image back to its original state because the energy is only 10% of original LCD backlight energy. And this is another example. Okay, before, after, before, after. Okay, before, after. before, after, before, after, before, after. Okay, before, after, before, after. Okay. Now here we try to maintain the image such that it look natural. All right. And in a few years back, we published a paper which adjusts the brightness of the image, and it works fine. However, the color doesn't look natural for some images. Right? Then I have another student working on this, and finally we apply this anchoring theory to solve the problem. It works beautifully. Okay. Now, one nice thing about this technology is that it's so simple. It's just apply a filter, to the image, and that's it. Okay. Forget about all this theory in the background. It's so simple in terms of actual operation. And I believe that people in consumer electronics like things to be simple, right? You like simple things. Okay, so what's the next? In this line of perceptual video processing, I also did some work on perceptual video coding. Okay, and here's one example that we want the end device, the terminal device, to be simple. Okay, now there's this famous DVC technique, distributed video coding, and we know that DVC is DVC encoding is very light. It doesn't involve that much computation. However, DVC decoding is computationally very heavy. Okay, so our idea is this: let's put the simple things on this terminal, okay, and transfer all those heavy computational tasks to the cloud. So the cloud is going to do some transcoding to convert DVC to, for example, H.264. Now for H.264, the encoder is computationally expensive, but the decoder is computationally very light. Okay, so hopefully all the light things are equipped on the terminal devices, but all the heavy computational work is done by the cloud. Okay, so here in the cloud, you have to do DVC to H.264 transcoding. Now transcoding is an old business. I think most of you may have done that already. So what's new here? Now we try to apply this JND concept for the transcoding. And the reason is following. Because for any transcoding, the main challenges are the following. First, how do you design the second stage encoder given that the original video data are unavailable? Okay, so this is the transcoding part. Okay, the input is this. This is your input. Here, the output of DVC is the input to the transcoder. However, you don't have the original input, right? So if you do any optimization and compare the output to the input, it's not actually the same as the original input. So our idea is the following. Let's try to this output look as if it's the original, perceptually the same as the original, right? And this is the best we can do because some sort of distortion already happened here. That's something that you cannot get rid of, all right? But we can guarantee that the output of this transcoding will be the same as its input perceptually, okay? So let me show you some results. This is the output of JM 17.1, okay, for transcoding. This is our result. So the question is, can you see any difference between the two images? Silent. Hey, that's the answer I want. You cannot see any difference, okay? Then this is the output of JM 17.1. This is our result. You probably can notice some difference, but it's very minor. So it's perceptually identical. Okay, this is a football sequence. This is the output of JM 17.1. This is our result. Okay, similarly, for Foreman, this is the output of JM 17.1. This is our result. Okay, so let me draw a conclusion here. What I have described, what I try to emphasize here is that purely signal processing, algorithm may not be enough for many of the tasks. If we want to really improve the image quality, you have to take the perceptual properties of human visual system into account. Okay? In my own experience, I found this anchoring theory a very powerful tool. It can be applied to many problems. I gave you two examples here. One is about the ubiquitous projector, and the other one is about the LCD image enhancement under low backlight. Okay, and now by the same kind of thinking, then you can apply perceptual properties of human visual system into video coding as well. I personally think that we have MPEG 1, MPEG 2, MPEG 4, and now H.65. Okay, now they claim to be twice better for each new generation of video codec. Then will we have a new generation of video coder which is twice better than H.265? Now, if it can happen, how can we do it? And my theory is that we pretty much, are beating the meat now. Okay, by conventional information theoretic approach, you can only go so far. If you want to any breakthrough, then it has to be a perceptual approach. Okay, and I think just like many other researchers in the video coding community, I'm also trying to do something along the line. Okay, now I promise to show you, if I have time, I promise to show you some of my work in music emotion recognition. All right. Then this is the interface we built. Let me show you a live demo here. I have a test bed installed on my computer. As you can see here, it's loading the songs. And there's a total of 1,200 songs in my database. And this is the interface. We classify the emotion of the music by two parameters. One is called arousal, and the other one is called valence. Okay? The arousal, if it's a very exciting sound, then the arousal value is high. If it's happy sound, then the valence value will be high. If it's a sad sound, then the valence value will be low. Right? So instead of search music through titles, or names of the singer, then I can use this kind of interface. I specify what is the emotion I want. Now suppose I click here, then all the related, all the songs of that kind of emotion will appear. Then I can choose whether I want to hear this, I want to listen to this, or I want to listen to this. Okay, most of these songs, all these songs will have, emotion close to the point I selected. So in this approach, every song is mapped to a point in this space. We call this emotion space. It's two-dimensional space. It's two-dimensional because we want it to be applied to our smartphone. Our smartphone touch panel is only what? It has only 2 dimensions. Okay? So we thought this is a very good application for that. Now let me try this. It's supposed to be calm music, like slow music. And let's listen to some of it. Can you hear the music? Okay, good. This one or this one. You could tell right away, songs in this quadrant are much kind of slower than the previous one. Or this one. Okay, they say that I like this music very much. I want to, I want to know what is the emotion distribution of the songs sung by this singer. Then I can do this, artist, and these are the songs sung by this singer. Okay? Then furthermore, if they say, I want to create a playlist, then I can just draw a line in this space that represents a playlist. The song can be played from this point all the way down. And of course, we can offer some option for the users to edit this playlist. And there's no limitation to all these possibilities. Okay. All right, so that's some work that we did in effective computing. What I have shown you here, this is just interface. This is the easy part. Now, our research is the thing that's in the background, the engine. that computes and recognizes the emotion of the music. Okay, let me close it. And then what is the, let me move on to other applications. Oh, okay, this is a movie poster, Hobbit. I have been working with the company Red Digital Cinema in LA, in Hollywood, try to help them solve some of the autofocus problems. Okay, and let's look at this video clip. It's called Steadycam. It's oops, how do I get to that? Hold on. So let's watch the video. Can you hear the music? Okay, let me stop it. It should be this one. This one. Let's try it. Okay, let's see if it works. Oops. No sound, huh? It doesn't work. Again, let's forget it. Yeah. Thanks. Well, this video plays better with sounds. Okay, well, great, enough. Thank you. So this is what it appears. Okay, you have a concert, and this is the final result you see on the TV if it's broadcasted on the TV. Okay, and let's see how it was actually done. It's called high tech, huh? So you see two people there. Okay, one is the cameraman, and the other one is called puller. And what he is doing is to, kind of turn a knob, that controls the focus of the camera. So when I first saw the video, I said I got to do something about it to make it automatic. All right. So the technique has to work for Hollywood. Excuse me. And you know that Hollywood people are very, very picky, and their eyes are different from my eyes, to be honest with you. They have very special eyes, and they can pick up any minor, very slight difference in the final output video. So the issues have to be addressed are, first, the autofocus technology has to be fast. Autofocus has to be fast. Second, it has to be accurate. Okay, and then it has to be stable. You don't want the image to appear blur, then sharp, then blur again. Okay, you want it to be constantly improving. Okay, so in terms of speed, and accuracy and stability, let me show you some results of our technique. Now, the first one is I call it close range performance. Our technique can work at very close range. It's the same technique, one single technique. All the demo I show you today is based on the same technique. Okay, we don't do patches. Okay. So you see how close they are. There's a scale back there. It's about 1 or 2 centimeters, and yet we are able to take good images of the scene. The second one is about, this is also close range operation. This is the default technique of that particular camera. And autofocus, in my view, is the most challenging problem for digital camera. It's very challenging. Okay. And then let me see the other one. This is for the scene change. Hope hope you like our results. And then this low light condition. You may feel that iPhone is the best smartphone in the world, but let me tell you, they have very lousy autofocus. For most of the phones you have, or most of the phones I saw in the market, the shortest distance is about 6 to 7 centimeter. That's the best you can get. We try to cut it down to 3 to 4 centimeter, and we believe we can do it. Our limit is the actual, the limit of our method is the actual limit of the optical device. If the lens can be imaged at, let's say, 3 centimeter, then our autofocus technology can deliver that kind of performance without any degradation. Okay, so this is for object tracking. Again, you have to tell me if you are not happy with this result, then my student will have to stay in the lab for 1 more year. Okay, this is a comparison with Sony HDR FX1. The camera was about 9 years ago. That was top of the line at the time. Okay, I spent more than $3,000 US on this device. It's a high definition at that time. One of the first high definition cameras. Okay, this is the speed of our technique. And this is try to mimic this litro type of functions. That means refocus functions. Using the regular autofocus technology. Okay. And then this is another thing. This is called blooming effect, right? If you point your camera at a light source, then it's very difficult to do autofocus. And on the right is the original method of the camera, and on the left is the performance, is the result of our technique. Okay. All right, and this is a live field camera we built several years ago. And the paper was published in SIGGRAPH some time ago, 5 years ago actually. So let me show you some of the results. It's a single camera which can acquire the depth, which it also allows refocus. And what you see here is a multi-view function. Okay. And the camera, let me go back. The camera, we call this programmable aperture camera because we try to capture the light field by changing the aperture of the camera. We use an LCD like this. In this case, it's 5x5 array. By open up some of the squares there and close some of the squares, by changing the pattern, we are able to capture the light field, and this is the result you see. Okay, and this is refocus. I kind of displayed the images from the background, by focusing on the background all the way to the foreground, by displaying the sequence of images. All these images are computed after they are captured. So this is very similar to litro. Okay, so I guess I'm going to stop here, and to entertain you with some answers. Yeah. Any questions?
Any questions?
Yes.
And how would it apply, for example, for more dynamic situation like a video or let's say the background is changing?
Okay. Yeah, you are asking the same question that the CTO of HP asked me, some time ago. The computation, as I told you, is log n. I'm sorry, it's order of n. All right. You basically go through the images once, and that's it. Okay. Each time is like an filtering operation, so it's linear to the number of pixels you have. It's very fast. For video, it's the same. Okay, and the result doesn't have any flickering in it. No flickering artifact. Okay. Did I answer your question? Okay, good. Yes, another question here.
Yeah, I appreciate very much such an elegant, informative talk. And my question is related to kind of the commercialization of your innovative technologies. I can convince easily by your result. Like you say that your focus function is much faster than what Apple iPhone can do. And have you done something, try to sell your technology to kind of iPhone supplier, provide the camera? I think you can convince them quite well as you just did.
I think I need your help on that. Yeah,
I try to.
I try to. You know, I think most of the work I did have great commercial values.
Yeah.
All right. In fact, I spent, in the last 2 years, I spent a lot of time trying to push the technology forward so that they can be used by the industry. I have mixed feeling about it. Okay, to be honest with you. Okay. I remember, 11 years ago when I, came back to this country. I quit my job in the U.S. and returned to this country, and I thought I should do something for this country, especially for the industry, because professionally I grew up in the industry, in the U.S. industry. But I said that I have mixed feeling because most companies here want things free.
Okay, that's not fair.
They don't want to pay. They want things free,
Okay.
right? So I ended up spending a lot of time explaining my technology to them, but at the end they say thank you, and that's it.
Okay, that's kind of
So
surprising.
it's a very sad experience. But I had some successful, examples, successful cases. One of the largest camera module manufacturer in Taiwan is testing our technology. In fact, I'm going to do it this afternoon. Okay, I've been working with them in the last 3 months. Okay, so they're going to use it in their production line to speed up the testing.
I see.
Okay, and I don't think I can tell you the number, but it's going to be, it's going to improve their production, reduce their production, testing time by at least 70%.
I see.
Yeah, so that's one successful example. Another successful example is that one famous company in the surveillance business in Taiwan, they also adopted our autofocus technology.
I see.
Yeah.
Okay, I observe you are still very persistent in commercialization your technology, and
I try to,
hope
but,
you can do better and with very success stories. Thank you.
Yeah, but I do need your help.
I hope I can help with everybody here. Okay, thank you very much.
Yeah. Yes, please.
So I had a question with regard, first of all, to the projector with the camera. So what sort of camera could you just use, like a cell phone type camera, fairly inexpensive one, in a projector to do that, or you need something that's a bit more expensive? I was curious.
Okay, it really depends on the images that you want to project on this. If it's a simple image, then a webcam type of camera module will be good enough, right? If it's very sophisticated, like this, with very fine details, then the resolution has to be high enough, comparable to the image texture.
Okay, so it depends upon what the projection is.
Depending on the
showing,
image,
yeah.
yes.
And then the second question is Mr. Emo an application that you can find online?
Actually, the whole thing was ready 4 years ago, but we've been very hesitant to put it as an app because there could be some licensing issue. Okay, licensing. Copyright. I'm sorry, not licensing, but I should say copyright.
Copyright.
The big five, or now it's big three. Big five are very, very sensitive to the copyright.
But you're just using somebody's. You're not actually changing their content. You're just creating a way of making playlists, aren't you?
Yeah, but it may involve some transmission of the content. Okay, and I don't have the permission to do that.
Oh, yeah, so if you analyze the content to try to get...
Analyze is okay,
yeah.
But transmitting the part of the content is difficult. For example, if you want to use my technology, then I have to apply all these processing on your songs,
right? Yeah.
And you have the collection of songs, but I don't, right? I have to know what you have. Now, suppose all the computation is done on the cloud, then I need to transmit those songs into the cloud, right? And that may infringe the rights there.
But couldn't you just have analyzed songs, and then you could, You know, you
That can be done, yes.
and then you
that
just
can be done.
access it. I've got my music,
That
and
can be done.
I just
And
do a match.
then all I have to do is just transmit the song ID
Right.
to the server. Yes, that can be done that way. In fact, we are pursuing in that direction.
I think it'd be very. I'm very interested in that.
Sure.
When it's
Can you help me commercialize this technology? Okay, good. Thank you. Yes. Yes.
Hello, Reggie Little from California. Just a general question. In theory, I know a lot of applications where people are interested in using techniques like this for navigation instead of just projection type stuff. So the idea would be, say, in environments where GPS is denied, could any of these methods be employed as an alternate way of doing navigation? That's a huge problem area that people are looking at.
I'm not sure about that for navigation, because here I don't have any information like GPS does. Right? I don't have that.
But yeah, there's a lot of interest in maybe recognizing scenes and focusing on things in a scene, and maybe mapping that to areas and telling where you are. Where the idea of being able to map very quickly, focus very quickly, recognize things very quickly on the fly.
It could be. No, it could be. It can be used as a supporting technology, but I'm not so sure about whether it can be the main technology though, because we are not doing recognition. You know, we're trying to do enhancement of the image quality. Yeah, and quality counts in my experience. You know, I remember the days when I worked with this video phone group in AT&T. So that was like 20 years ago, in the mid '90s, right? The second generation of AT&T video phone. You know, at the end of that, I got tired. Because I'm dealing with very crappy image quality, and then I think the final result, you know, in terms of the sales, you know, results, tells us that quality really matters. You know, it has to be good quality, and that's why I'm now working on this perceptual video coding stuff. All right, try to hopefully without increasing the bandwidth, you can improve the video quality. Yeah, and we know that you know, 60 or even 70% of the internet traffic is on video these days. Yes. Yeah. Yes, Professor Carl.
Hi, can you hear me?
Yeah,
Okay.
sure.
I'm talking about your autofocus performance. You just show us the performance of your, the autofocus. So could you give us some little bit information about what algorithm, what method did you use for autofocusing?
You mean what technique Apple used for autofocus?
Your method.
Oh, my method?
Yeah.
Okay, sure. I can tell you a little bit of it, but I don't think I can tell you everything about it, okay? Because we have two patents on this, US patents on our autofocus technology. But from research point of view, I can tell you what it is, okay? Now, we found that the critical thing there is the kind of the sensitivity, all right? The method has to be sensitive to the location of the lens, all right? If you plot the sharpness of the image when the lens moving from one end to the other end, all right, then the profile is like this. The shape of this image sharpness is going to be like this, right? And so the name of the game is this, right? Suppose you are somewhere on the curve. How do you get to the peak position as fast as possible? Okay. Now, if the initial position is in the flat area, then there are two directions you can go, either that direction or this direction. Then how to make the right direction? So that's very important. Okay. Now, in this slope area, you want to go very fast. If you have to know that I'm on the slope, right? And no peak is there. So you have to have a good method to estimate the in-focus lens position. Okay. And our methods target this kind of issues, right? Now, it turns out that, what should I say? it turns out that now when the lens in this in-focus lens position is very, very sensitive.
Yeah, right.
All right? And because it's so sensitive, and that's why you see kind of bouncing effect, the bouncing effect, right? Blur, a little bit blur, and then sharp, and then a little bit blur. Hollywood people don't like this, okay? And that's why they turn to, they use our technology. We can kind of fix the lens, lock the lens on that position. And how do we do it? We do some mathematical analysis of the problem from sensitivity point of view, okay? And with that, we are able to reach the peak very fast. Yeah.
Okay.
Okay, may I have one more question here?
Sure. You can have 10 questions. Since you're the
I don't think I have
host.
sufficient time. My question is on the color compensation. In that case, I would like to know, theoretically, can we always have a perfect reconstruct result, given a scenario that we have a sufficient energy of the projector, theoretically?
You mean sufficient energy in terms of computational power, or?
Yeah, in terms of sufficient energy
No, the
on
answer
the
is no.
projector.
You cannot really reconstruct the original scene. Let me use this chart to explain it one more time.
Because I always can see a subtle difference from your reconstruct
Yes,
result.
yes. Oops, it's dead. Thank you, Bill Gates. I like Bill Gates so much. Anyway, remember I have a chart there, right? Try to show you the gamut, right? Now, for a surface like this, right, it has its own gamut, right? If you shine anything on it, then the image is going to look kind of brownish, for sure, right? And so that means the image gamut is not completely within the projector's gamut, all right? And the gamut means that it's the color that the projector can produce, right? So you have something outside its projection area, I mean the gamma area. Right, so you cannot completely reproduce the original image. There's no hope for that unless the original gamut is within the projector's gamut.
So that's the difference that causes the subtle difference.
Yes.
Oh, okay. I see.
Yes. Yeah. But here we try to preserve kind of the perceptual appearance of the image. Right. Now our eyes have this amazing capability. Now you probably have heard this chromatic adaptation capability. Right. We can adjust so that an off-white surface may appear white to you. Okay, it's because of all this adaptation capability of our eyes. Okay.
Any other questions? I think that's about time. So let's give our big hands to Professor Chen for this wonderful talk.